All right, let's talk about fog now. Fog is a cloud that has its base with the ground, with the Earth's surface. So instead of the cloud surface being way up high in the atmosphere, the surface of the cloud is the surface of the Earth. And so we are able to interact with the cloud down at the ground. So what defines fog is the restriction in visibility. So if the visibility is restricted to 1,000 meters or less, it's fog. Otherwise, it's called mist, which is like a light drizzle. One type of fog is radiation fog, and it sounds like something kind of to watch out for after a nuclear holocaust or something, but radiation fog has to do with radiational cooling. So as the Earth cools at night, it causes the air close to the ground to cool off, and if it's a humid environment, that humid cool air can reach its dew point temperature. And if the dew point temperature is reached, then the humid air will begin to condense onto nuclei, or in this case, things near the surface. So the condensation nuclei can be located close to the surface, and in this case you would also have a lot of dew on the things at the surface, the leaves, the grass, the fences, the cars, and so on. But the fog that forms, and you see the picture here, is called radiation fog because of the way that it's formed. There's also advection fog. Remember, advection refers to the horizontal movement of air. And so with advection fog, if you have warm air that is advecting or blowing over a cooler surface, again, it's a cooler surface, so it can cause the air to reach its dew point temperature. And once it reaches that dew point temperature, condensation occurs and we have fog develop on the ground. So this is typical if you've been to the Great Lakes area around Michigan and the Midwestern part of the country. You have warmer air passing over the colder water surfaces, and some fog forms right along the lake area. Another type of fog is called steam fog. This is also referred to in the Arctic areas, Arctic sea smoke. It develops in the fall or winter when it's getting very cold. So we have very cold, dry air that flows over a large body of water that has not yet frozen. And as that happens, some of the water evaporates into the cold, dry air, and it can cause the lower part of that air mass to condense. And so we get these wispy kind of clouds, or fog rather, that forms right over the surface of the water, like you see in this picture here. So it looks almost like there's smoke coming off of the water. Another type of fog is called upslope fog. It develops on mountainsides or hillsides when air is forced to rise up for some reason. And as the air is forced to rise, it can cool to its dew point temperature, and at that point we get fog forming. We see this a lot in Sedona. I'm not sure about Prescott. I have never been there. After it rains, typically in the winter, you see this when it's kind of cool and we have a rainstorm or a snowstorm. We get some low-level clouds that develop on the around the red rocks. So the rocks are kind of shrouded in this mist, and it's formed in this way. So air is forced to rise up the high points, in this case the red rocks, and as it rises it reaches its dew point temperature, and so we get fog because it's still touching the Earth's surface. It may not be right next to the ground where you are, but you could climb up that hill and encounter the fog. So let's look at the comparative sizes of these things that we've been talking about and will talk about here. Here's a typical cloud condensation nucleus, remember, on the order of 1 micrometer. And once condensation occurs on that surface, it becomes a cloud droplet, and it can continue to grow into a large cloud droplet. and it can continue to grow until it reaches a raindrop size. When it becomes a raindrop, as we'll see here in just a moment, gravity takes hold of it and it's able to fall from the cloud to the surface of the Earth. So let's talk about precipitation now. Precipitation refers to water in solid or liquid form that falls from clouds to Earth's surface because of gravity. So we don't just call it rain, we call it precipitation. Rain refers to liquid precipitation, but precipitation can also be frozen, like snow. Terminal velocity refers to the constant downward directed speed of a droplet due to that balance between gravity acting downward to pull it toward the Earth and the air resistance that keeps it up in the cloud. So this is why the water droplet becomes large enough, the cloud droplet has to grow large enough before gravity can take hold over the air resistance and pull that water droplet down. So how do water droplets form? How do cloud droplets grow to the point where they can be big enough to fall to the ground? So in this picture here, we have two little sized dots. The tiny ones are cloud droplets and the bigger ones are raindrops. So with the first process here, it's called collision coalescence, and this happens in a relatively warm cloud. So we get the condensation occur the way that we've already talked about, and then when a little cloud droplet gets a little bit bigger, it starts to fall through the cloud, and as it falls it collides with other little cloud droplets and they coalesce, forming even a larger cloud droplet until it grows large enough to the point where gravity can pull it down. So collision coalescence happens in warmer clouds, and the name of the process describes what's going on. Water droplets, or cloud droplets rather, collide and then coalesce to form raindrops. The second method is called the Bergeron-Findus process, and this happens within a cold cloud. So we're higher in the atmosphere, the air is colder, and we have some freezing nuclei. And so what happens is we get ice crystals form, and once ice crystals form, they begin to fall, and as the velocity increases, the crystal is going to grow. Again, it's going to interact with other cloud droplets, similar to what we saw with collision coalescence, and cause these ice crystals to grow even more. But the main difference here is that these are ice crystals as opposed to water drops like we saw with collision coalescence. So the ice crystals grow, they continue to get larger and larger, and then gravity takes pull of them and they fall down to Earth's surface, and they may fall out of the cloud, or they definitely fall out of the cloud as ice or snow, but they may not reach the surface of the Earth as snow. We'll see in a moment what dictates that. There's different forms of precipitation. It can be liquid, it can be freezing, or it can already be frozen. So liquid precipitation is what we call rain or drizzle, and the difference is really the size. You can see the different sizes here for rain and drizzle. And rain are the bigger drops, and the bigger the drop, the more unstable it becomes, and it tends to break apart into two or more smaller drops, and so we don't get gigantic, buckets of rain. Well, that's an expression, but let's say gigantic water balloon sized raindrops. They break apart before they ever get that large. So this kind of liquid rain we're going to see mostly from our nimbostratus and cumulonimbus clouds, the big rain producing clouds. Drizzle is just a really small kind of spitting rain. So you maybe need an umbrella, you maybe don't, depending on how tough you are to not get wet. So this type of rain, drizzle, usually occurs in stratus clouds. So you get that big gray sky just covered with stratus clouds, and then to add insult to that injury, you get this drizzle kind of spitting down on you. Freezing precipitation refers to freezing rain and freezing drizzle, and frozen precipitation refers to snow pellets, snow grains, ice pellets, hail, things that come down as solids. So what dictates whether it's liquid or solid when it reaches the ground? It really all has to do with the air profile between the cloud and the ground. So up here in the sky, we've talked about now how clouds form and how we can get through the Bergeron process, in this example, these ice crystals to form in the clouds. So we know that any precipitation that's falling at that height in the atmosphere is falling as snow. If the air profile stays cold between the cloud and the ground, in other words freezing, then that snow from the cloud will fall as snow to the ground. However, if you have warm air somewhere in between the cloud and the surface of the ground, it's going to cause a melting of some or all of the snow that's falling from the clouds and change what's happening down at the ground. So if we have just a little wedge of warm air, like we see here, somewhere between the clouds and the ground, the precipitation falling from the clouds is snow. It encounters this warmer air, and some of that snow melts. It becomes rain again. It goes back to its liquid form. And then here's the freezing line between that warm air mass and the cold air mass. Once the now liquid precipitation comes back into the freezing temperature, it refreezes. Some of it refreezes, some of it may not. In this example, we have a deep enough level of cold air that it's all freezing, so that by the time it reaches the surface, it's sleet. So not big fluffy snowflakes, but little bits of sleet that may accumulate, may not, depending on how much of it's falling. The next one we'll look at here is freezing rain, and if anybody has encountered freezing rain, you know that it can be very dangerous. It's basically coating everything on the surface of the earth with a thin layer of ice. And you don't always see it. You can step out your door and it looks fine and normal out there, but as soon as you step on the ground, it's ice. I grew up in Indiana, so we had freezing rain quite often. So same process up here. The precipitation falls as snow, and then it encounters warm air, so the snow melts into liquid precipitation, and it remains liquid until it reaches the surface, where just the surface of the earth is cold. So the things that make up the surface of the earth and the air just right around the surface here is freezing, just enough so that as this liquid rain encounters the surface that it lands on, it freezes on impact. And so it's not snow, it's not sleet, but it's just ice down here. And then finally, if we have a completely warm air profile between the cloud and the ground, it could be a warm summer day, and up in the sky we have a snowstorm, but down below, because of this warm air profile, the snow has melted and it's falling as rain. So you wouldn't see this kind of thing happening with thunderstorms typically. Thunderstorms fall out of the sky as liquid or hail, as we'll see. This would be more like Bergeron process precipitation that starts off as snow and then ends up as rain. So here's a profile of freezing rain. Again, here's a picture that shows some damage. It can cause these big trees that get weighted down with the ice that forms on them. So you get a lot of broken tree branches as well as a lot of traffic accidents. Here's soundings, the air temperature soundings and dew point temperature for freezing rain profile. So higher up in the atmosphere, the dew point temperature and the air temperature are separate, but you see as they come together closer to the surface here, they are together and they're below when they encounter precipitation or water in the atmosphere, they send a signal back to where the signal came from. So it sends a reverse sort of echo and allows the software to create kind of a map of where these returned microwave signals are coming from. So here's a picture of a typical radar station. So inside of this big ball would be the dish that's transmitting and then receiving the return signal. And the data that comes from these is used on a map like you see here. This shows radar reflectivity with echo intensity shown by color. So the closer we are to the red, the more intense the rain, the stronger that it is that we're seeing rain. So we're seeing here it looks like a squall of thunderstorms, very severe weather that would probably be happening in the summer. And then further away from that, still some rain, but less intensity. Doppler radar is a special type of radar that uses velocity or the Doppler effect to determine in a little more detail what's going on with precipitation. So it takes advantage of the shift in frequency of sound and electromagnetic waves from a moving source. So Doppler radar can detect a frequency and shift. So you can see here the shift would be what direction is the storm coming from. So it tells us not only where is the rain, but also what direction is it moving. So here's a Doppler image. You can see the closer we are to the green side of colors, they indicate motion towards the radar, and then the reds indicate motion away from the radar. So we can get a sense of what direction this storm is moving or circulating. It may not just be moving, there could be some circulation within the storm that's useful to know. So it can tell us how developed a thunderstorm is, or if there's a tornado involved in there, and so on. Measuring precipitation amounts takes place through what's called a rain gauge. And these are typically cylinder type devices like you see in the picture here that are specially calibrated to read how much precipitation has fallen. And the precipitation can fall as liquid or snow, and we can still get an accurate reading. So a lot of these types of gauges require a person to come in and read. There are some newer gauges that don't require a person to read the value. They're done digitally. And we see precipitation values given in some of our weather reports. So if you're monitoring weather data, maybe from the Prescott Airport or somewhere nearby, no doubt they have a rain gauge and they can tell you how much precipitation fell within a 24-hour period.